Ever wonder why a seared steak tastes completely different from a boiled one? Or why your sauce suddenly splits into an oily mess? Here's the truth. Every time you cook, you're running chemical experiments. Your stove is a reactor. Your ingredients are molecules waiting to transform. And the reactions happening in your pan are the same ones scientists study in labs. But instead of beakers and Bunsen burners, you get dinner. Today, we're unlocking the hidden science behind cooking, the chemistry of heat, flavor, and transformation. By the end, you'll never look at your kitchen the same way. Let's start with the most delicious reaction of all. We're going to explore 3 big ideas today. First, the Maillard reaction, the browning magic that makes food taste incredible. Second, how heat actually moves through your food in 3 different ways, and why it matters. Third, the chemistry of flavor balance, salt, acid, sweetness, and fat, and how they work together like a molecular orchestra. Along the way, we'll bust common cooking myths using real science. We'll see why some techniques work and others fail. And we'll discover that great cooking isn't about following recipes blindly, it's about understanding what's happening at the molecular level. Ready to become a smarter cook? Let's dive into the chemistry of browning. Why does toasted bread taste better than plain bread? It's all thanks to the Maillard reaction. When you apply heat above 285 degrees Fahrenheit, amino acids and sugars in your food start bonding in hundreds of new ways. This creates complex flavor compounds, nutty, savory, slightly sweet, and deeply satisfying. It's not caramelization, which only involves sugars. The Maillard reaction needs proteins too. That's why a seared steak, golden brown cookies, and crispy roasted vegetables all share that irresistible richness. The reaction happens fast on the surface, where moisture evaporates and heat concentrates. No browning, no depth of flavor. It's chemistry you can taste. So how does heat actually reach your food to trigger this magic? Heat doesn't just appear in your food. It travels, and it takes 3 different routes. Conduction is direct contact. Think of a steak touching a hot pan, heat moving molecule by molecule through the metal into the meat. Convection is heat carried by moving fluid, hot air circulating in your oven, or boiling water swirling around pasta. Radiation is heat traveling as invisible waves, like the infrared glow from your broiler or grill. Each method cooks food differently. Conduction gives you a crispy crust. Convection cooks evenly all around. Radiation can char the surface fast while leaving the inside tender. Master chefs instinctively use all 3. Now you know the science behind their techniques. But heat alone doesn't create great flavor. Let's talk about emulsions and sauces. Ever made mayonnaise or hollandaise and watched it suddenly break into greasy puddles? You just witnessed an emulsion failing. An emulsion is a mixture of 2 liquids that normally don't mix, like oil and water. To keep them together, you need an emulsifier, a molecule with one end that loves water and one end that loves fat. Egg yolks are packed with these. Mustard has them too. When you whisk fast enough, tiny oil droplets get suspended in water, stabilized by emulsifier molecules acting like peacekeepers. But add oil too fast or let temperature spike, and the emulsion collapses. Foams work similarly, air bubbles trapped in liquid by proteins. Whipped cream, meringue, and even beer foam rely on this. It's all about molecular tension and balance. Speaking of balance, let's explore the chemistry of flavor itself. Why do professional chefs keep tasting and adjusting? Because flavor is a balancing act between 4 key players: salt, acid, sweetness, and fat. Salt doesn't just make food salty, it enhances other flavors and suppresses bitterness. Acids like lemon juice or vinegar brighten dishes and cut through richness. Sweetness rounds out sharpness and balances heat. Fat carries flavor molecules to your taste receptors and adds creamy satisfaction. When one element dominates, food tastes flat or harsh. But when they're in harmony, every bite feels complete. Think of a great vinaigrette. Oil for richness, vinegar for brightness, a pinch of salt, maybe a touch of honey. It's chemistry meeting art. And plenty of cooking myths are based on misunderstanding this balance. Let's bust some of those myths next. Here's something wild. Baking soda can make your onions caramelize faster. How? It raises the pH, speeding up the Maillard reaction. Meanwhile, adding acid like wine to beans while they cook can actually slow down softening by strengthening pectin bonds. Marinating meat in yogurt or buttermilk tenderizes it because acids and enzymes break down proteins. And that sear to lock in juices advice? Totally a myth. Searing creates flavor through browning, but it doesn't seal anything. Water still escapes. Even resting meat after cooking isn't magic. It just lets juices redistribute as proteins relax. Every cooking trick has a chemical explanation. Once you see food as molecules in motion, you start predicting what will work and what won't. But not every kitchen rule holds up under science. Let's separate myths from truth. Myth: wash mushrooms and they'll get soggy. Truth: mushrooms are already 90% water. A quick rinse won't hurt them. Myth: alcohol completely cooks off. Truth: even after an hour of simmering, some alcohol remains. Myth: oil in pasta water prevents sticking. Truth: oil floats on top and does nothing. Stir your pasta instead. Myth: cold water boils faster than hot. Truth: physics says no. Hot water has a head start. Here's a real one. Salting water does raise its boiling point, but only by a fraction of a degree, not enough to matter. What salt really does is season the pasta from within. Chemistry clears up confusion and makes you a more confident cook. Now, let's test what you've learned with a quick challenge. Pause and think. If you're making scrambled eggs and they turn out rubbery, what went wrong? Too high heat, which caused proteins to squeeze together too tightly, pushing out moisture? Next question. Why does adding cream to tomato sauce sometimes make it curdle? The acid in tomatoes can destabilize milk proteins, especially if the cream is cold. Solution? Temper the cream first, or use higher fat cream, which is more stable. Final one. You're baking cookies and they spread into flat puddles. What happened? Probably too much butter or sugar, not enough flour, or the dough was too warm when it hit the oven. Every kitchen mystery has a chemical answer. The more you understand, the more control you have. So why does all this chemistry actually matter in real life? Understanding food chemistry doesn't just make you a better cook. It reduces waste, saves money, and improves nutrition. When you know how heat and time affect vitamins, you can cook vegetables to preserve more nutrients. When you grasp emulsions, you stop throwing out broken sauces. When you understand browning, you unlock deeper flavors without needing expensive ingredients. Restaurants, food manufacturers, and even space agencies use this science daily. Chefs like Heston Blumenthal and J. Kenji Lopez Alt built careers on it. And at home, it means fewer failures and more delicious experiments. You become less dependent on recipes and more intuitive in the kitchen. Cooking stops feeling like guesswork and starts feeling like creative problem solving. But even scientists don't have all the answers yet. What's still a mystery? Believe it or not, we still don't fully understand why some flavor combinations work so well together. Scientists are mapping flavor networks, but taste is deeply personal and cultural. We're also still learning how cooking methods affect the gut microbiome and long-term health. Does high-heat grilling create compounds that are harmful? Or can other foods neutralize them? Researchers are investigating. There's also mystery around fermentation. We know bacteria and yeast transform food, but predicting every outcome is still part art, part science. And the perfect texture? That's subjective and hard to quantify. Food science is evolving fast, with new discoveries every year. The kitchen remains a frontier where chemistry, biology, and culture collide. So, what's next for you as a cook? Let's recap. Cooking is chemistry. The Maillard reaction creates rich, browned flavors through heat. Heat travels by conduction, convection, and radiation, each with different effects. Emulsions and foams are all about stabilizing tiny droplets and bubbles. Flavor balance comes from salt, acid, sweetness, and fat working together. And many cooking myths crumble when you understand the science. You now have the tools to experiment smarter, troubleshoot problems, and cook with confidence. Want to go deeper? Try one new technique this week and observe what's happening at the molecular level. If you enjoyed unlocking the science behind your kitchen, hit subscribe. We're exploring more hidden science in everyday life. Drop a comment with your biggest cooking question. Thanks for watching and happy experimenting.